Hello and welcome to day 11 of the Advent of Code 2021. My name is Jacob and I will walk you through the solution that I implemented in Kotlin right now, explaining along the way how I arrived at it. Once again, as always, if you already know the puzzle, please use the chapters below to skip ahead straight to the solution. Otherwise, I will not read this right now from top to bottom, but at least explain what the idea of this puzzle is if you have not seen it yet. I'd say let's jump right into. One thing I quickly want to mention is I do have a Discord server as well to keep in touch a bit with you. So if you're interested in that, to chat a bit, discuss something, ask questions obviously, then you'll find in the description you'll find a link to that, as well as on the channel page itself. So yeah, please consider joining. Right, the puzzle of today is the following. We are having octopuses, or is that actually the plural of that? I'm not so sure, but it says here that hold like internal energy, and once they reach a certain energy level, they will like emit a light flash. And the important thing right here is it's pretty similar if you know Conway's Game of Life. It's quite similar to that. And so if they do flash, they will cause all the surrounding octopuses. So there's this grid right here that we have of the octopuses. They will cause all the surrounding ones to also gain one level of energy. And now you can probably already see what this can lead to. If you have one that emits energy to the surrounding ones because it itself reached the level where it flashes, and the surrounding ones, due to this energy increase from that one neighbor, now also flash, you can have a chain reaction. So you could like have a single one that then causes a chain reaction since all of them flash and affect their neighbors and so on and so forth. So what you simply receive right here as the input is this 10 by 10 grid with all the octopuses, so you know who are their neighbors, and of course the integers here are the current, like the starting energy level. Energy levels go from 0 to 9, meaning that once you reach anything over 9, or rather you reach 10, that would cause a flash of that octopus. And then it propagates to the neighbors, increasing theirs by 1 as well. Two things that are still important right here before we can jump into the code is that once an octopus flashed already in one like step, so to say, so we do this in like steps that we simulate in a bit, it cannot flash a second time, because the reason I guess is more or less obvious. Otherwise, this is like a circuit breaker of sorts. Otherwise you can have like an infinite loop somewhere that if you're unlucky, they all cause each other to like go back and forth all the time and flash, like cause each other to flash all the time. So what we do is once an octopus flashed, we like set its internal energy level to be 0, and also for this round, so to say, then for this step, it cannot increase anymore over 0, only like the next step. Right. I think this is everything you need to know, and let's jump into the code. So as always, let's first look at parsing the input. One thing that's important here, I reused some code from day 7, I believe it was. 9, I think it was day 9, where we needed also a grid. If you haven't watched that, first of all, obviously recommend to watch it. It was actually a pretty nice puzzle. I enjoyed implementing it. I will quickly cover what this grid class that you see right here, which I originally implemented back then, is doing. But I'll make it quick. If you want to know more about it, go to that video. So to parse the input, we obviously split by a new line character again, such that we get. So you see, actually today the input is similarly sized, or actually the same size to the example, which is quite rare. Usually you get like a very small example and then a ginormous actual input. Today, not so. Split obviously by multi-line, such that we get each row of the values. Again, split by nothing. Filter out is not blank. Pretty much the same we do every day by now, such that we get like each individual character. So these would be like the rows, the inner lists, and then the outer lists would be each row, so to say, the lists inside. Now the thing that is now important here is that we have this octopus class. So you see, for now, ignore that it takes this cell, which just like comes from somewhere. What the hell? I'll explain obviously what happens here in a moment. The other thing that is pretty easy to understand is we just take the value and cast it into an integer, which is the starting energy level. So now let's look at the octopus. So again, it's down here. It receives the cell. Look at in a moment, and the energy level in the constructor. You see, this is it is private, but it's also var, so it is mutable, since obviously later on we need to, well, increase the energy level. What else does this class have? It's not a data class, but a regular one, since I anyways need to override equals and hash code, as you see in a moment. So yeah, data class doesn't make a huge sense, a lot of sense. There's no other feature that I would need from it. The other things that we have here are a few more fields. So we simply have will it flash. I made it a field. If you watched the previous video, actually there I said for the opposite, hey, a field here would be nice, but I had a method. So I figured today, you know what, let's do that. So I have a getter, which simply, well, it behaves like a getter in Java, but it's still a field, but it's also recalculated like a getter. So every time we call this field, it actually runs this function, so to say, such that the value can be dynamic. Otherwise, of course, if you do this, it just instantiated once, and then this is never going to change. So in this case, yeah, it's recalculated. Will flash obviously simply means if our current energy level is higher than 9, we will have to flash that octopus, or it itself has to do it. And then did flash again is mutable. It's simply if in this step it did already flash. The other functions in here are check if it now has to flash, which obviously is quite easy. If we will flash, then we call the flash function, which we'll take a look at in a second. Otherwise, we return an empty set. Why an empty set? We'll also see in a moment. We have reset the flash status. It's simply after like a step, and then we obviously have to, for each octopus, say, okay, you reset your status if you did flash, since in the next round it can flash again. So that's that. And then the final public function right here, increase energy level, which just adds energy to the current level, which by default is 1, since that's what it wants. But I figured there's a nice reason example here to take a default value actually. The flash and adjacent flashed, let's look at in a moment, similarly to the why the hell we return a set of octopus here from just a single octopus. For this to understand, we have to look at the grid. So this already looked quite funky here right now, and even funkier is if you look at the return type. This is maybe a bit over-engineered, overkill, but I think this makes for very generic code first of all, and also very easy to read code later on, because you will see in the end it kind of reads like an English sentence almost at the end, or like a text. So what we return here is a bit confusing. Maybe it's a list of lists, so this is simply the row and columns of lambda expressions that receive a grid cell of octopus. Again, we'll look in a second what that actually is, and returns an octopus. Why the hell would we do that here? Kind of overkill, right? We could in theory just return an octopus. That's what we want to parse. But you'll see in a moment why I opted not to do that. For that, let's have a quick excursion into the grid. So grid, again, if you want to know the details here, I'd suggest watching the day 9, where I go over all the details of this. The only things that are important right here is, and it changed like slightly from back then, is that to construct it, we receive exactly the same type signature that you saw from parsing the input. And we then say generate our matrix, which simply creates a bunch of cells with the X and Y coordinates. The important thing about a cell is, which is a class down here, is that it's like similarly to yesterday, it's like self-contained in a way. So it knows which grid it is part of. So cell simply being like, yeah, well, a cell at one XY coordinate, you have one cell. But the nice thing is the cell knows what grid it's part of, so it can like look up its neighbors pretty nicely. It is private though, because we don't really want that someone from the outside can tell us. Only the cell should know. Obviously, the thing it also knows its own coordinates, since well, that just makes sense. And finally, now it comes in what you saw here, which looked a bit funky, which is this value constructor. So this is simply, you see the same type that we have, that we received the list of lists right here. So what we do when we generate the matrix is we create a cell here with this, the grid, the X and Y coordinates, as well as this value constructor, which is inside. And then here what we can simply do is, well, create this whole thing. And the important bit now comes here. So all of these things are parameterized, they're generic. So a grid can hold, like in each cell, can hold any value. That is what I changed also to the previous one, where it was just always a grid of integers. So if you go back now to day 9, actually, I retrofitted that to now also be, to just have a grid of int, right? Which is what it wants anyways. In this case, yeah, it's parameterized because it can hold anything. Same, of course, with the cell. So the cell just mirrors that, because what is in the end what the cell holds is precisely this value right here. So you see the value, what actually is in the cell in the end, the integer from the day 9 or today our octopus, is the t right here. If you're not familiar with generics in Kotlin at all, yeah, this takes way too long to explain now. If so, please let me know. I'll be happy to make a separate video about that. So what we simply now do is we invoke this lambda expression right here. So this value constructor that we received, passing in our self and receiving back. That's what you see here. We pass in a cell of t, which is just what we just constructed. So this, and we receive back the same kind of t. So now we have our value right here, and we just have a field, well, to access the value. Why the hell did I do this? The reason you might have already noticed, because now whatever this value might be, the cell first of all doesn't have to care and also doesn't know really what this t is. It's an integer, is an octopus, is it whatever, can be anything now. The nice thing is that now whatever value we have in here can know which cell it is part of. Reason being, of course, that then it can use the functions of a cell, right? Because it can know, hey, I'm part of this and that cell. I can use like its functions. Currently only get adjacent, but that's already pretty useful. So get adjacent, what it does, literally what it says, you can say, do you want to get diagonal neighbors as well? And it will just return you a list of all your surrounding cells. So if we look at this here and we say get adjacent of 1 with diagonally true, we would get like 2, 5, 2, 3, 3, 8, 2, and 1, since that's surrounding that one, right? Yeah. Then the thing that we now need to look at is on the other side of the coin, what happens if we pass in ourselves right here. For that, let's go back to day 11 and look at the octopus class, because this is now where this comes in, right? If we parse the input, we receive or we return these lambda expressions. So regularly, of course, you would have returned like just the octopus, and then here also just return a list of octopus. In this case, we return this lambda with the signature that we see right here. So we receive this cell, and now comes to the interesting part. This is not yet bound to anything, right? It's just like a closure at this point. So at some point we will receive some cell, and now comes the cool part. We pass this to our octopus constructor, such that obviously the octopus now here has access to which part of the cell it is. And because the cell knows which part of which grid it is, you can trace back where everything is, so to say. It's like one big tree of data at this point, which allows for the code later, the actual like logic, to be very lean, so to say, and very like easy to read. There's not a lot of loops going on anymore or finding neighbors or whatever. It's all nicely hidden away behind these interfaces. Which I personally value a lot. This is a bit funky to do it like this, but I figured it's quite nice. So in the other case, actually, with the integers, we do just simply nothing with this. So we receive a cell where we just say ignore it, we don't care, and we just return the integer for day 9, that is. In this case, we want a cell because we obviously need to know what our octopus neighbors are. If this doesn't make a whole lot of sense, if you still didn't quite get how this works, please drop me a comment. I'll try to elaborate a bit further. Right, so once we have the input, I figured we do have the grid at this point, so it's like a generic grid of octopus now, which is quite nice. But we're actually not really interested in the grid itself. What we're interested in are the cells. So the grid has a cells field that just returns you all the cells ordered, just going like through the grid. And we're actually also only interested in each value. So now you know that the value of each cell is an octopus, which means that if we do this expression, we get back a list of octopus due to this the t, obviously. So because this is generic here with the t, this in the end it is octopus in this specific case. So all of these where it says t is then octopus, such that compiler knows at this point, hey, this has to be a list of octopus. And now we just do our simulation. So I because I need to know well, actually in this case I don't need to know the step, but I did it with a range in this case here. So we start with step 1. Weirdly, it doesn't start at 0. Would have been a bit nicer maybe, but that's fine. Starts at 1 and it goes all the way to 100. Important here, we use the dot dot operator such that we get both, including the 1 and the 100, right? Since otherwise we only iterate for, let's say, 99 steps. Then we do a sum of, since we want to sum how many octopuses flashed. So this is in the end what we have to return for part 1. There's a lot of examples here, but in the end we just want to return how many total flashes are there after 100 steps, right? So we just sum together each time how many flashed for each of these steps. So what it then specifies on the page, what you have to do firstly in each step is just increase the energy level of every octopus in the grid by 1. Here, first, the energy level of each is increased by 1. Obviously, this is like the starting ignition, so to say, to the chain reaction, right? If you wouldn't do this, since there's nothing yet, there's over 9, it would never like start doing anything. And essentially, once you did that, yeah, it's the rest here is like self-sustained or whatever. So we just do octopuses for each, it increases energy level. And this is what I meant, which I very much value about Kotlin, and which is why I coded it in this way. This now just reads like an English sentence, right? Which is very beautiful in Kotlin. So just, yeah, my mom could understand this. Octopuses for each, it increases energy level. Like, yeah, that is, if you add a few more filler words, is literally a valid English sentence. What we do next is we have to find all the ones that did, in fact, flash in this due to this increase. So what we do is we do this check for flash. And now comes the part in where we return the set. So we want to have a set of all the octopuses that did flash. Why did I do this? Simply for the reason such that the counting at the end, how many did flash in this iteration in total, is like completely, like any arrows are taken out of the equation because we have this set. So instead of having like a counter integer or whatever and adding to it, you then have to take care, well, did this octopus already, did I already count it, or was it like affected due to a chain reaction or whatever? If you do it like this, you know that if you just return everything that did flash somewhere in the step, because it's set and it's deduplicated, you don't have to care at all. You don't care when they flashed or what order or whatever. We just are interested in how many in total are in this set, and it will automatically discard any duplicates we might have returned. And then, of course, this is what we in the end sum by here. Before we check this, the last thing we then do in each step is also octopuses for each it reset flash status. So we, of course, have to now say, okay, the step is over, so you can flash again, such that when the next iteration begins here, yeah, it's eligible to flash again. Right. Last thing we have to check, and I think then we're already done with part 1, is check for flash. So what happens here is, well, this you already saw. Obviously, if this specific octopus did not flash, because if will flash is false, we can just return an empty set immediately, because, well, we know at this point this one definitely did not flash, so yeah, empty set. I guess that makes sense. However, if it will flash, we just do that. So the one thing I added here, just to make sure that we don't have a weird bug, it is also private, so it's not like anyone from the outside can call this. I still added this require here, so we only do the actual like mutation of the state of the octopus that does the flashing, only if we have to flash. So we require that it will flash, otherwise we throw an exception with this error message here. Will never really happen because this is the only place where it's called is after checking that already, but it's a good practice. So what happens if the octopus flashes? Obviously its energy level goes to 0 that we saw, and now we have to say, okay, it did flash in this step, such that it cannot happen another time. And then once the step is over, due to this reset thing, this goes to false, so it can do that again. And then you see here that obviously this returns back to the like outside logic. So what we here have to return is obviously also a set of octopus, but in this case now it's like recursive of sorts, or like also folding. So obviously we have to return a set of ourselves, since we literally just flashed. That's what we did here. Plus, and now comes in the chain reaction part, we get all the adjacent octopus, and this is precisely where this weird setup with the cell value constructor and stuff comes in, because we have reference to like where we are within the grid, and the cell knows where it is in the grid. We can just say cell.getAdjacent, and you actually see the cell again ask the grid to get the adjacent ones for these coordinates, which it knows. We will, and in this case diagonally, this is something I forgot to mention, in this case it does want that you also look at diagonal ones. So with this flag we can just simply enable that. So we ask the cell, hey, give us the adjacent one. The cell asks the grid, hey, give us what is adjacent to my coordinates. And then we receive this right here. And then what we simply have to do is just tell all, it's like a messaging chain. So I model it in a way that it is really how you read the text as well. So it just tells now all the adjacent ones, hey, I flashed, do something about it or not, but here's the information. So what we just now say is, it in this case is the cell, so the value to the generic t is the octopus. So each lambda here has one of the octopuses, and we just tell it, hey, an adjacent one of you flashed. We don't care really that it was this one, doesn't matter, it just needs to know, hey, something around me did just flash. And then we call this, and obviously what we check is if we did not flash yet, we increase our energy level by 1, which is just the effect that was described there. And this is where this obviously becomes important. Otherwise you can have that it just infinitely flashes back and forth, right? So once you did flash, once you did this already, you in this step at least, you will keep at energy level, stay at energy level 0. So that's important. Otherwise though, we might have been at 9, let's say, at this step. So we increase it, which means that in the next line now we would be at 10. And if you look at will flash, energy level is now greater than 9, so we will actually flash. At this point, of course, we're in a different octopus, so this is maybe a bit confusing. Like what we call here is not the same one as this anymore, obviously. So now we just again call flash, and now you see where the recursion, chain, whatever comes into play, because each octopus always checks, hey, do I also flash? If yes, I tell all my neighbors that I did. Then all the ones that did already flash in this step, due to this thing right here, will not do it again, because this will then be false. Or they will flash again, which in the end causes all of the neighbors to be notified. For this, a visualization would be really nice, that you see a bit more what is going on here. Yeah, but that's a bit out of scope. Otherwise, of course, if we just increased our energy level, or maybe even not, but we do not need to flash, we again say empty set is returned because we didn't flash. And the last part here that is important is that we then flat map over all of these sets of octopuses, because now of course we have like a nested set of sets, which we need to flatten down to just a flat set, and simply add ourselves to this as well. So in the end, what this returns right here, or rather what this check for flash returns, is all the octopus that, due to this initial like signal of, hey, check if you self or flash, that were flashed anywhere in the same chain reaction. And yeah, and due to the fact that we have a set, and outside it's also a set, it automatically again discards the ones that were that might have been part of something else as well. what we just check here to make sure that it's what is the equality, so to say. I decided that a cell determines equality. So if two octopuses are pointing to the same cell in the same grid, because again the cells equals and hash code is looking at the grid and the coordinates in there, then we can conclude it's apparently the same octopus. If it's the same cell in the same grid, yeah, no reason to believe it's not the same octopus. Of course, we could have looked at energy level, but it's not really necessary. Right. So then once we are here, we have all the octopus that did flash. And again, here we also have the flat map, right? Because we ask every octopus, hey, check if you flashed. Each of them return a set. So we would have a set of octopus, or actually a list of set. So we can flatten it, and then we have to convert it to a set, because this will otherwise be a list, which is the default of flat map. And then, yeah, we have our octopus that flashed in this step. Right, the rest we already looked at, we reset and we count how many there were, and in the end we sum all of that together, such that we know how many flashed in that round. Let's maybe put a breakpoint right here and quickly run this to have a bit of a better understanding what is going on there. Right, so you can see right here that in the first step actually nothing flashes. We have just an empty set. Yeah, since if we look at all of our octopuses, there's none that were already at 9 beforehand. Now there's some, of course, that are at 9, or not of course, but there are now some at 9 due to this increase. But then were none beforehand at 9, so it doesn't flash anything in the first round. However, if we continue once further, there are a few that you saw were at 9, so they now went to 0 because they did flash already in the previous line. And you also see now that we had 55, in fact, that flashed in this round. Right, let's quickly, and yeah, we can look at it if you want to. Obviously, they will all have energy level 0, and you can also all see here by the reference numbers that they're all different octopus, which the set nicely takes care of. We can also quickly look inside of one of these to see how this works. So we're at energy level 6, so we won't flash. So essentially here the chain reaction stops because we return an empty set, and we don't notify anyone else, so it like collapses back down. Here it would be maybe interesting to like see the stack trace, but you can tell a bit here already. So you see that we had 2 times the same flat map here apparently. So we flashed already once. Now we have one that is now at energy level 10, apparently, since we increased it by 1 in the previous line, which means that it will now flash. So it will call someone else that will that will flash. So let's put our breakpoint right here and look at that. So we reset it to 0. Did flash is now true, and will flash obviously is false because, well, we're not at the threshold. But we will now call all of our neighbors again and ask them if they also need to flash now. So you see this was apparently a neighbor of it. Actually, you see it by the coordinates. And in this case, again, the chain reaction stops because it will not flash, so it returns an empty set. And then obviously this is just, if you have a bunch of empty sets, they obviously just result in like, yeah, nothing, another empty set once flattened. So this is how this works. Let's look at part 2. So what we need to do for part 2 is we need to find the first step, so to say. This time not only doing 100 steps, but infinitely many on paper. We just need to find the first one where all of the octopus just flash at the exact same moment. So they set it up in a way that this will happen at some point, such that you see right here, you have like, you increase the energy level and they're in exactly the right setup, such that at this point you will cause like one huge chain reaction, and they all flash at the same time. So what we now have to do is to find which step, and this is what you return here, what is the first step during which all octopuses flash. Sounds a bit difficult. It's super easy though with the setup we have. It's like one of the easiest part 2 ever. Took me like, I don't know, 2 minutes or something. This is literally a copy paste of this code here. We could have put it into something, but there's one small difference, which is why I didn't. In case, instead of doing like 100 iterations right here, 100 steps, we do infinitely many. A perfect use case for a sequence in Kotlin, which is lazy. If you don't know what a sequence is, I have a full video, Kotlin collections versus sequences, so give that a watch, where I elaborate all, well, what is a sequence, how does it differ to a regular list and a set and so on, and what are each ups and downsides. So yeah, make sure to watch that if you're interested or you simply don't know what it is. But in essence, it's a collection that is lazy, meaning that you only generate the next value that comes next in the sequence once it is actually needed, which means that you can have infinite sequences, because you can just say, okay, make this only ever give the next value when we need it, such that you can iterate into infinity. Of course, it doesn't work, right? You need to stop somewhere, but this is perfect here because we want to iterate into infinity because we don't know how many steps it takes. Might be 100, might be 1,000, might be 1,000,000. We know sometimes at some point it will happen, but we don't know when. Obviously, for this also a while true loop would have worked very nicely. It's the same idea in essence. But this is way more idiomatic in my opinion, also because now what we can do is use the first method. So what we simply say here is start with 1. So we still count like how many steps does it take. And then for each step, we say take it, which is similar to like a folding operation that you saw in the previous day, plus 1. So we start with 1, and then after that, we simply always say, now do 1 plus 1, we have 2, and then the it is the previous 1. So then we do 2 plus 1. Yeah, so we just get an infinite sequence of increasing numbers, increasing values. And now what we can nicely do, and this is where it is very idiomatic, we can say, give me the first one of these sequence values. So that is the step in the end, which is where we return it immediately. That is true. And true in this case being, this is literally the same code as above. I guess you could put this into a method, actually. Why not? We could just get simulate, I guess. Why not? And even ask us, do you want to get rid of the duplicate? Yeah, we do want to do that. So now we just return how many we flashed, and we still do our steps right here. And then in the previous step, we can now put this into 1. So we just say count how many were flashed. Although now at this I don't like, because now it's very weird to see what actually the variable is like. So this looks a bit better. And in this one, as you now see, same code as here. The simple thing we have to do to find out if all flashed in the same step is to simply say, is the count, the amount of the ones that flashed, equal to all the octopuses we know about, right? Simply meaning that every single octopus we know about also flashed. We could also even do, because it's already a set of octopus, instead of counting, we could also do something like this, if this would be also a set, because then it would also be the same sets even. That would also work. So all the octopuses are contained in this one, but counting is just as fine. And then we know that this is the case. And the way this works now, of course, is that we just like try a value by value, 1, 2, 3, 4, 5, and the first one where this expression is true, meaning we have as many flashed ones as we have total octopuses, this infinite generation of values stops, and we return whatever the current value was, which is precisely, obviously, since we started with 1, the current step. So in this case, that would be 216, I believe. So we can quickly run this as well to see how this works. But that's that then for part 2. So yeah, this was one of the nicest to implement parts 2. I guess there would have been like other ways to do this where it would have been way more difficult. But in the way I did it, luckily, I have to say, of course, we don't know beforehand, it was super straightforward. So you see right here, in the, let's say, second step, we have 55 that flashed, but we have 100 octopuses. So, well, obviously 100 is not equal to 55, so definitely not all of them flashed. And then we just continue. I'm not going to do it obviously until the end, but you see that it never works out, meaning that we continue and continue to generate new values until at one point we reach one step where in fact all of them did flash, and that then is 216. So that's part 2 of day 11 of the Advent of Code. We even did a nice refactoring here that I didn't spot initially. If you have any questions about something, don't hesitate to drop me a comment below. I'd be very happy to answer them. And if you're also participating, please consider joining my leaderboard just to have some competitive fun. You'll find the code to join in the description of this video. Apart from that, thanks a lot for watching. Consider subscribing to the channel, and I see you on day 12. Tschüss.